Okay, let us recommence. So, at the end of last time, introduced the theoretical entity, because we're in probability theory, not just talking about how do you deal with data. Theoretical entity of what happens when each thing that you could sample from this random thing has more than one number associated. So that means instead of calling the thing a random variable, sometimes we'll call it a random vector, because it spits out more than one number. So for example, if that random vector has two numbers it spits out, then you would describe a probability, a continuous probability distribution, or a density, using something like this. So it would be designated not p of x for a density on a single variable, a univariate density, but it would be p of x comma y, or p of the vector x, if you prefer. And so for every possible little x and y, there'll be a probability density, just like there was for univariate ones. So for univariate ones, we just do a curve saying, here, oh, that's a terrible one. Better one. For univariate densities, you would just draw a curve, as we've looked at. That's not much better, is it? Like this. So the y-axis is probability density, meaning it's probability per unit x-axis, where actual probabilities are area under the curve. That will be the probability of getting a value between here and here. Now, while we're in two dimensions, again, the z-axis, which is brightness in this version of displaying it, and is height in this version of displaying it. Those are just different ways of looking at it. But that is again density, and instead of being per unit on the x-axis here, it's per unit area in x and y. And so talking about probability now will be, you got to look under this thing and calculate how much you have. So instead of being area, it'll be volume. But it's all the same idea. It's just now been generalized to two dimensions and can be generalized to more than two. But now let's talk about manipulations we can do with these multivariate densities. Okay, so a density is again going to be, you put some random variable in here. Here I put an arrow on it just to emphasize the fact that the random variable is a vector. And in the previous slide it was a vector with two coordinates, but in general it can have any number of coordinates. And you can still talk about things like mean and covariance and what happens with linear transformations and so on, just as we did with data. So with data, you just had a matrix which was your list of data. And last week, the last thing that Arrow did was for sets of data, what do we mean by the mean? What do we mean by the covariance? How do we calculate it? How do we think about it? Using linear algebraic and geometric intuitions that we've developed across the semester. But if we're going to talk about a continuous n-dimensional probability density, thinking about it like a vector is a little hard, because now it's this continuous entity. But the calculations are all pretty much the same idea. It's just what used to be sums or averages or whatever now become integrals relative to probability. So the expected value is, you wanted, the expected value of a vector is now going to be the same formula, kind of an integral of that vector, probability of that vector, d that vector. That's what we wrote for expectation. But this is funny notation. What do you mean d a vector? If you took calculus, if you remember calculus, d is relative to some scalar number. So d a vector means I have to go this way and this way and this way, and however many ways across the vector to do this integral. It means, what I really mean is an integral n times of the vector x1 to xn, p of that vector x1 to xn, dx1, dx2, dxn. So if you wrote it to calculus, it turns into this big ugly thing. However, it turns out that if you think about this, you're averaging, you're taking a vector, you're multiplying it by a number, so you're getting these things, and then you're averaging across all the possible vectors. Well, x1 is only governed by P of x1. x2 is governed by P of x2. So by the time you get done doing this, it turns out the expected values are kind of being done separately for every coordinate. Okay, I won't go through a big, ugly math proof. Many people in the room would prefer I avoid calculus whenever possible, and here it definitely it's avoidable. But one way to think about this is to go back a slide and say, if this is the thing I'm trying to calculate the expected value of, in 1D, expected value of some distribution, I'll write some obscure one, is where can I put a fulcrum and balance this thing? Okay? That was the intuition of what you meant by an expected value, whether it was data and that up top was a histogram, or whether it's a theoretical entity and it's a density. Expected value is just where does this thing balance? Over here, expected value is where does this thing balance? It's just a two-dimensional thing. It's the centroid. And if you did take physics in high school, the centroid is just the average value this way and the average value this way, which is exactly what this slide is saying. It's just expected values for each coordinate alone. Okay. Covariance. So covariance is how do the different coordinates covary? Now, this formula isn't exactly true. I've left something out here, and I've left it out of the rest of the slide. What did I leave out? When you calculate a covariance, what's the first thing you do? We did it with data multiple times. You probably even had it in homework by now, I expect. In the data version of covariance, what outer product do you compute? Your data with itself, or do you do something to the data first?
Center it.
You center it. So covariance is in fact the expected value of x minus mu x, x minus mu x transposed. So it's an outer product, and it's a whole bunch of expectations. It's a big matrix. By the time you're done, it's a big matrix where you're asking, how does, what's the expectation of x1 minus mu x1 squared? What's the expectation of x2 minus mu x2 squared? Over here would be what's the expectation of x minus mu x1 times x minus mu x2. This is going to get ugly fast, but it's a matrix filled up with things that look like that. Okay? Just like it was for sample data. I've simplified it over here just because it makes the notation and the stuff that I'm talking about a little bit easier to understand. So remember, this is a vector. It's a random vector, but it's still a vector. It's a set of numbers. And when you take, and it's a column vector, because that's our standard for vectors is they're going to be column vectors. So I have a column vector here times a row vector, just like I did for covariance with data. And when you have a n by 1 times a 1 by n, you get an n by n. Okay? So the covariance is a matrix as big as, on either side, as the number of variables in your multivariate density. And each entry is like what we did for data. It said how do the data go together, but now it's not data, now it's this theoretical density function. Okay. What happens when you transform data? I said all this stuff at the very end of last time, but I wanted to work through it because we were running out of time. What happens when you transform random abstract entities in some linear fashion? Well, transform in a linear fashion means multiply by a constant, dot product with a vector, multiply by a matrix, that kind of a thing. So the most general version is what happens when we multiply a random vector by a matrix. Okay? And so what is matrix times random vector? So, matrix M of any shape that's appropriate times a random vector, well, appropriate vector shape means that this has to be n. So this is M, and this is X, our random vector, X1 dot Xn, okay? And so a matrix multiply is going to give us a new vector, M times X, and any entry, whichever one I want to pick, is a dot product, which means it's a weighted sum of these guys. Okay? So any one of these entries is basically, you know, let me say that this is entry I, say. So that means I take sum of over j of mij xj. That's just matrix multiplication, right? This is a constant. This is a random variable. It's a piece of a random vector. And we're doing a weighted sum. So, what this says right here is that I can pull capital M out. I can pull capital M out because I'm taking the expected value of this thing, and we already have a rule that says this is the same as the sum over j of mij, the expected value of xj. Expected values are linear. We already knew that. And so just applying that over and over again in all of the pieces of this output vector gives you what I wrote here. Okay? So expectation, even in the multivariate world, becomes this nice linear thing. You can pull constants out, you can pull matrices out. It also deals with affine, which means if I did a plus and a constant vector, I could pull the constant vector out of the expectation also. That's not on the slide, but it's also true. Okay, what's a covariance? So covariance was defined up top as just an expectation of an outer product. Okay? So if we're going to do this linear thing, then that's just a new random vector, this random vector as opposed to this random vector. And so the covariance of this random vector, again, assuming it's centered. So I didn't subtract off the means everywhere, but so we're either assuming they're zero or you can add that to the notation and make it look uglier. Okay? So the covariance of this is going to be an outer product of this with itself, which is what's written right here. And matrix algebra, the transpose of a product is the reverse product of the transposes. That's written here. Okay, so this is an expectation of matrix times random vector times matrix. And the constants get to get pulled out for exactly the same reason. I proved that you can pull the first one out, proved just by the intuition of the expectation of a sum as the sum of the expectations. You can also pull the late one out for the same reason. I didn't write that down, but it's the same thing. So in other words, this formula you've seen before. You've seen it for data, right? Where we're taking a covariance of some data matrix. So what I'm saying is, all those things that we developed for analyzing a set of data, now that we're going to these theoretical continuous distributions where the way you calculate everything is these ugly integrals and so on, all the rules still apply. Okay? And we're going to use this stuff quite a bit. Okay, other things you might want to do with a multivariate distribution. So here's a distribution, but suppose we only cared about x. So we have this. We have some model about something's going on in the brain and the neurons for something that we're interested in, but we're only interested in the response. And there's a bunch of other variables in our model that aren't relevant to the response, but are inside our model. So we want to ignore them and just get what's the probability of the response being this versus the response being that. So we're interested in variable x, and we actually don't care about y. So we might want to take this density and sometimes one uses the word project it onto the x-axis. It's not project like linear algebra. So Arrow tends to prefer the term, we're going to take this two-dimensional distribution and smash it onto the x-axis. Just smush it down there and say, what's the probability of different x values? I don't care what the y value is. And so the way to do that is, the probability of getting this x value is the sum, the probability density. I should be careful with my language. Remember, the probability of any given value is 0. So this is density. The probability density of any given x value is going to involve summing over the densities over all possible y values, which is exactly what's written here. So the probability density of any given x value is just integrate out the y values that you don't care about. Okay? So that's called a marginal distribution. And so effectively, what you're doing is, here's why I use the word projection, because you're basically kind of projecting down along vertical lines, summing up everything that you see above you. Okay? So you get a high value here because there's lots of stuff here, and a low value here because there's very little stuff here. Okay? So this is just a pictorial of that integral. Do you have a question? Are you confused? Sure? I know you guys don't interrupt me enough. And I repeat this, you never interrupt me enough. I go way too fast, and I know that. But the way to prevent it is to interrupt me. So just another call for interrupt me as frequently as you can. Okay, so that's the marginal. Another thing we often do with these densities is rather than say, I don't care about y, or I don't care about x, say, I care about a particular y. So that's called a conditional distribution. It says, what is the density of x, given that I already know that y equals, say, 90. Okay? So now we're throwing all this stuff away. We did that conditional idea. Oops, it's not notated yet. Now it's notated. Okay, we did this idea with the deck of cards. What's the probability of a jack? 1 in 13. What's the probability of jack given that it's a heart? 1 in 13. Or what's the probability of it's a heart given that it's not the jack of spades, or whatever examples I used. So we did conditional probability theory when we did the deck of cards and discrete distributions. This is just the continuous version of the same thing. And it's the same rule. Yeah, it's the same rule, i.e., the way you get a conditional is to take the density itself divided by the density of the thing that we're assuming is true. Remember, probability of A and B divided by probability of B is probability of A given B. I'll write that down rather than just say it out loud. What we had on the slide on Tuesday is that probability of A given B is defined as probability of A and B divided by probability of B. That's how we defined conditional back when we were doing decks of cards. This is exactly the same formula. A and B, B. Okay? So B's the thing after the conditional, the thing that you're assuming is true. We're living in this world. Other Y's aren't happening. Only this Y is happening. So we've restricted our attention to when Y is true. So we have to normalize by the probability density of Y. Okay? So that means we have to first compute the probability of Y, which was the previous slide. That's a marginal. That's, in this case, rather than smashing it down, we're smashing it to the right. Okay? And saying, what's the probability of Y? Now take any given value, divide it by that, and that's the probability of X, given that we're restricting ourselves to this one little row, this one little slice. Okay? So these are things that we talked about in discrete distributions. We've now introduced the analogous thing for continuous distributions. So this probability X and Y, this for various X's, so X is going to vary here because it's the probability of X. This is going to be a function of X. So across all the X's, this is this slice of the joint distribution, ignoring all the rest of it, which we don't need because we know we're on this slice. And what's downstairs is the marginal. Okay? Same as what we do with decks of cards off on the left. Okay, so that's a conditional. What did I just add? Oh, yeah, so this is... so now you see the statement of this, which looks exactly like what's over there. What just got added? Oh, is that what it? Yeah, that's what it just got added. The graph came back. Okay, there it is. Fine. How do we manipulate conditionals? We manipulate them typically using what's called Bayes' rule. This is Bayes' rule. And I'm going to prove it to you on the next slide. But first of all, why is this so important? So what it allows you to do is, suppose there's some conditional probability you're interested in. So example, we're trying to fit some parameters to some model and fit them to some data. So I got some data here, and I got an abstract model that I think models my data, but that model has parameters. It's got, what's the probability of hitting the wrong button by mistake, and what's the, how good are you at this task? Something like, what's your ability? What's your, mean expectation of percent correct? So it's got some parameters, some numbers that I don't know. I have a general model, but it's got some numbers that describe how it'll behave. All right? And I'd like, what's the probability of a particular set of parameters given my data? And I have no idea how to do that. On the other hand, if I knew the parameters would totally define how the model works, and different data sets would now have probabilities associated with them because the model would tell me that. So sometimes one of these conditionals is easy to figure out because it's the way your model works, but when you flip it, that's what you actually want to know. And so Bayes' rule lets you use the opposite conditional probability plus some normalizing factors, which we'll talk about in a subsequent class, to learn something about a conditional probability you'd like to know. So where does Bayes' rule come from? It comes from the definition. So here's just the general version of it. So we're living in this world this is the same Venn diagram when I defined conditional probabilities in the first place. So a world of all sorts of things could happen. A could be true or not. B could be true or not. They could both be true. Neither could be true. Okay? And the definition of a conditional probability was P of A given B is P of A and B divided by P of B. And the definition of P of B given A is P of A and B over P of A. And if you take those two statements together and move the P of B to the other side, so P of A and B is P of A given B times P of B. What did I just do? P of B goes to the other side. P of A and B is P of B times P of A given B. That's this one. But if I reverse the roles, it's this. Okay, because I could have written the definition of this and then move the guy to the other side, which means this is equal this. And if this is equal this, now I can move P of B to this side, and I get P of A given B is P of B given A, that's P of A over P of B. That's Bayes' rule. So it just came directly out of the definition we've been using for the last few days. All right? But it is incredibly useful, and we'll be using it off and on for the rest of the semester. Again, this whole course is cumulative. So you really want to know this rule because it's ridiculously useful. Okay, so this will come back. In fact, it will come back at multiple times, and even today, I expect. Okay, so we've talked about conditionals, we've talked about marginals. Marginals are when you take this whole density and smash it down onto the axis. So that obviously takes into account not just this marginal, but this marginal and this marginal, all these marginals. Okay? So when we smash it down, we'll get something that, in this case, will be centered on 100. So that's the blue one. That's P of X, the marginal. But if we pick a Y value, notice that this is not a circularly symmetric distribution here. It's tilted, which means if I pick a Y value that's up here, now X is centered on a value other than 100. So the marginal, given that Y is 120, now has a different density than the overall, the conditional has a different density than the overall marginal. Okay? Which is to say that if you tell me the Y value, my opinion on X changes than if you don't tell me the Y value. Does that sound familiar? When is that not going to happen, this change of information? When X and Y are independent. Okay? We talked about independence for card decks. Probability of a jack is 1/13. Probability of jack given a heart is 1/13. So jack and hearts as events are independent. Now we're going to a more general situation where we're not talking about specific events. We're talking about random variables, X and Y. x and y. These are random variables. The combination is a random vector. If we're going to say random variable x is independent of random variable y, I haven't told you that I meant y equals 120 yet. I just said random variable x is independent of random variable y, which means we're going to want the conditional to look like the marginal no matter which conditional we pick, not just for a specific one. So the event y equals 120 is independent of x. That's what this is saying is false. Okay? If it was true, then we'd say the event y equals 120, if these were the same distribution, we'd say the event y equals 120 is independent of all possible x events. All possible x events. Okay? So we're doing something more general already, and we'll generalize that completely in just the next slide. Yeah?
I think I'm a little bit confused. So, are you comparing the blue and the green?
Right now I'm comparing the blue and green. The blue is the marginal,
Okay.
and the green is the conditional for this particular y value. And I'm noticing they're not the same, which means that when I told you y equals 120, that was informative.
Yeah.
It affected your opinion on x.
Okay. So
Now
then
back,
they're
let me
dependent.
finish this. Back when we talked about independence on Tuesday, we were talking about events. So in particular, right here, blue and green are different, which means the event y equals 120 and the event x equals 125 are clearly not independent. But what you see from this curves is actually almost all values of x as events are independent of y equals, are dependent on y equals 120. In fact, the only place where you don't learn anything is right at 100. Or no, it's not 100, it's probably somewhere else. It's yet something less than 100. Okay? So back then we were talking about events. I'm about to generalize that to random variables, which means you're not referring to a specific event, you're referring to any event that could have occurred. And so independence is going to be a much more general statement here. Okay? So back when x and y were events, like Jack and Hart, so the probability of Jack and Hart is 1 out of 52, equals the probability of Jack, which is 1 out of 13, and times probability of Hart, which is 1 out of 4. Okay, that was Tuesday, when it was a discrete distribution, it was cards. So this looks the same, and if you picked a particular x and a particular y, like x equals 110 and y equals 125 or something, this would be the same statement as last time. It would be independence between these two particular events. But if it's true for every pair of events, not just right here, but here, and here, and here, and here, and everywhere, if it's true all over the two-dimensional, or in the general case, n-dimensional space of your random vector, then you say those random variables are independent. They're always independent. No matter how x comes out, you telling me x doesn't change my opinion about y. And when that's true, this density, which is a function of two variables, will be separable. Separable is a nice math concept, but this is the definition of separable. It means I have a function of two variables which can be separated as a product of a function of the first one and a different function of the second one. This is true here. You can see it. You just multiply actually a Gaussian this way and a Gaussian this way, and when you multiply them, you get this pretty elliptical, symmetric between x and y thing. This is obviously not true of this guy. There's not a function of x times a function of y that gives you something that's tilted. When you multiply a function of x, whatever it is, times a function of y, you get something that looks the same in every stripe you're looking at. But here, that's not true. The conditional here and the conditional down here don't look like each other. The conditional down here is shifted way to the left. Okay? And so statistical independence on one of these plots is going to have a visual appearance where it looks like it's just aligned with the axes. Aligned with the axes. That sounds kind of familiar from linear algebra, right? This is not a matrix. This is a full continuous function of two variables. But aligned with the axes sounds like we're talking about something where we haven't rotated the matrix yet, right? Where we have an SV, where we have a diagonal matrix. So when we get to the Gaussian in a few slides, it will be all about the matrix is diagonal, just like it was for linear algebra. So some of the intuitions you have from linear algebra are going to translate to this. It's a much more general thing. This is just any old arbitrary function of two variables, and a definition that it can be separated into the marginal of x is, look, this is the marginal. P of x is called the marginal. It's the probability of x ignoring y. And this is the probability of y ignoring x. And if the probability of x and y is just the product of the individual ones, that means, and no matter which x and y you pick, that means that's what we're going to call independent. Okay? And it gives you, and it also does this thing, which we also did with cards. It says the probability x given y is just the probability of x, i.e. telling me y didn't change my opinion. So these were the two definitions we had when it was decks of cards, when it was discrete distributions. It's also true when it's continuous distributions, but now you don't talk about single events, you talk about the whole density functions, the whole distributions as being independent. Thus, this little caveat generalization here. If you haven't taken an abstract math class and never seen this upside down A, it means for all choices of. So this is P of x given y equals P of x, no matter which x and y you pick.
Question. So if you want to apply Bayes' rule, then x and y has to be independent?
No. Bayes' rule is absolutely true. It just comes from the definition of...
You kind of sort of divide.
No, hold that question because it's going to come... No, that's okay. Bayes' rule. Not have all this other visual noise as I write this down. Bayes' rule says that probability, and in the continuous domain, probability that x equals some value a given y equals some value b equals probability of y equals b given that x equals a, probability that x equals a over probability of y equals b. There's Bayes' rule written down. Okay? Still true. That's just a fact of events. However, if they're independent, x and y for all events are independent, that means that this thing right here doesn't depend on x, meaning I can delete the conditional. That's on the board right over there. And that means this and this cancel, which gives us a formula probability that x equals a given y equals b equals probability that x equals y, which also is a definition of independence. So Bayes' rule, once you give independence, just reproduces what we already have on the board. Doesn't depend on Bayes' rule. Bayes' rule is just a definition of conditionals. And independence says conditionals equal marginals. So if you apply that to Bayes' rule, you end up back where you started. Okay? All right. Special case. Suppose we have two random variables, x and y. And we define a new one, which is the way we're going to get a value of z is we're going to consult x and get a number, consult y and get a number, and add those two numbers. Okay? So a random variable is just a thing that can spit out numbers that follow some density. X has its own density, whatever it may be. Y has its own density, whatever it may be. And z is going to be defined as consult x, consult y, take the two numbers and sum them. Okay? So that's going to be a new randomly behaving thing. So let's look at how that randomly behaving thing behaves, because summing random variables comes up all the time. And so knowing how it behaves is worthwhile. So the first thing is, we already knew that expectations are linear for anything. So we didn't need to say anything about it, but let's write it out. It's actually worth understanding why expectation is linear in this continuous domain. So let's actually do it. Okay, so we want to know what's the expectation of z. which is the expectation of x plus y by definition. And x has its density and y has its density, and the events we're now talking about are xy pairs that we're going to sum. So that means to calculate an expectation, we're going to have to integrate over all possible little x's and little y's that might come up. And we're going to integrate the value of z, which is x plus y, that's the value of z, times the probability of getting little x and little y. Okay? Which is, integrals are linear, so it's going to be the double integral of x, p of x, y, dx, dy, plus the double integral of y, p of x comma y, dx, dy. Okay, so first let's do the second one first. Okay, so this is double integral. And we're going to the inner integral, this one right here, just this one, is integrate across x. Now, y doesn't depend on x, right? So it's, as far as that integral is concerned, it's a constant, which means just this piece is the same as integral of y, integral of p of x, y, dx, dy. See what I did? The inner integral is an integral of this thing, which we're integrating over x. This depends on x. This doesn't depend on x. So it's just a constant as far as that integral is concerned. So I pulled it out. What's this thing? By definition, a definition I gave you 2 slides ago. Take a bivariate distribution and integrate it over one of the variables. It's a marginal. What marginal is it? Right, I integrated out x, so it's just p of y. So this is integral y, p of y, dy. What's that? That was from Tuesday. What's that? Integral of y weighted by its relative probability across all y's. Say it louder. This is expected value. This is e of y. Okay? E of x plus y equals this plus e of y. This, I can do the same exact logic. All I have to do to get the same exact logic is do it in the opposite order, which with integrals you're allowed to do. So I'm not going to write out another one, but it's exactly like the first one. Okay? So, one thing you will notice, I used nothing about the form of pxy here. I did not assume, for example, independence. It doesn't depend on independence. Expected value is just simply linear. If I put a constant in here, there would have been a constant in here, it would have come out. It's linear that way also. So expectation linear, I've now just proven for you. Okay? This next bit requires independence. So let's figure out why it requires independence. Are you done with this? I get bored. Well, I want to do the expectation of the product. E of x times y. So that's, again, a double integral of the thing I want to take the expectation of, x times y, p of x comma y, dx dy. Now, it says if it's independent. So if it's independent, I can simplify this immediately by saying integral of x times y. What am I going to do with p of x comma y? If it's independent, what's that? What does this become? Yeah, you. What's our rule for independence of a joint distribution?
P of x times P of y?
P of x times P of y. It's separable. P of x p of y dx dy. Integrals only care about the stuff they depend on. I have one integral with respect to x. I have one integral with respect to y. So it turns out you can pull constants out with respect to one of the integrals, and by the time you're done, you get an integral of x p of x dx times an integral of y p of y dy. This is using some bits of calculus that may feel a little tetchy to some of you or poorly remembered, but it's basically, if we're integrating over y, we have something that doesn't depend on y, we can pull it out. And eventually we get to pull the whole thing apart, and this is e of x, and this is e of y. Okay? Now, why can't we always do this? So, I always forget that I need to come up with an example before I walk in here, because otherwise I'm going to make one up that's going to be false. Okay, suppose, yeah, I think this will work. Okay, suppose here's x. I'm actually going to go to a discrete rather than continuous because it's just much easier to think of this way. Suppose I have x is only taking on the value 0, 1, and y is only taking on the value 0 or 1. And suppose this happens 50% of the time, and this happens 50% of the time, and these never happen. So, x is either a 0 or 1, its expected value is a half. Y is a 0 or 1, its expected value is a half. Expected value of x times expected value of y is a half times a half, or a quarter. So this side, for this guy, is 1/4. Everybody with me? Okay, left-hand side, x times y is either 0 or it's 0. Because those are the only two things that ever happen. So the expected value of x times y is 0. So the formula failed. Why? Because these are not statistically independent. If you tell me y is a 1, I know x is a 0. Before you told me y equals 1, I didn't know whether it was 0 or 1. In fact, I had no idea. So these are statistically dependent. They're not separable. This distribution is not a distribution this way times the distribution that way at all. In fact, it's as dependent as could be. It's completely dependent. You tell me x and I know y. Y equals 1 minus x. Okay? So there's a counterexample. All right. Now we get to, with this fact and this fact, we get this one, which is the useful fact, which is what we want to derive, which is if random variables are independent, their variances sum when they sum. Okay? If you compute the variance of the sum of x and y, so what do you do? What is that? So here's x and y. I'm going to sum them. And variance is subtract off their mean and compute the expectation of the square of that. So here's the mean of x plus y, because it says that right up here. Okay? So the mean of x plus y is the mean of x plus the mean of y. Okay? So if you take a new random variable z minus the mean of z and compute the expected value of its square, that's the definition of the variance of z. Okay? So that this formula right here is sigma z squared. Okay? So let's derive why that's true using independence, which will be required. So we want the expectation of that big ugly thing. Expectation of, how many parentheses do I need? I need a lot of them. Let's do a bracket for this one. So we've got x plus y minus mu x plus mu y squared. Okay, that's what we want. Now, this is just, a plus b minus c minus d squared. So that's going to have terms in it like a squared, b squared, c squared, d squared, and it's going to have 2ab and 2ac and 2bd and whatever. That's just, take a polynomial and square it. Okay? I'm going to break it up into some pieces. And by the way, we're taking an expectation. Once we do that, we're taking an expectation of a sum, which is the sum of the expectations. Remember, expectation is linear, so I get to pull out pieces of this one by one. So, first thing I'm going to do is pull out the piece where all the things that are multiplying have the letter x in them. So I have x here and I have mu x squared. So this is going to equal, first thing, x minus mu x squared. That gives me the x squared, it gives me the mu x squared, and it gives me the 2 minus 2x times mu x. Okay, so that's some of the pieces. Not all of them, some of them. Then another set of pieces are all the terms that only have y in them, which I can conveniently get the same way, which will give me the y squared, the mu y squared, and the 2y times mu y. Okay? So far, so good. Which means all the stuff I left out are all the pieces that involve an x and a y. So there'll be a 2xy, there'll be a 2 mu x mu y, there'll be a 2x times mu y, and there'll be a 2y times mu x. Okay? So we're going to have all those. I'm going to write those down one at a time. So x times y, 2 of those. And they're both plus. Plus x times plus y squared. Okay? So we're going to get a 2 expectation of x times y. Okay? This is why I'm going to need independence. If they're not independent, I don't know what this is. But with independence, I do know what this is. So this is why this is going to work only if they're independent. Or it's going to be guaranteed to work only if they're independent. Okay, so there's the x and y. Over here, we got a mu x, and we got a minus mu x, and we got a minus mu y squared. Okay, so we got a minus mu x. Yeah, so the minus squared becomes 1, and so we're going to get a plus to expectation, but this is constants. So I don't even have to put the word expectation here because it's just a constant. So it's going to be a plus 2 mu x mu y. Then we're going to get some cross products. We got an x minus a mu y, and when we square that, we get a minus 2 mu y expected value of x. And we also have the y and the mu x, which will give me a minus 2 mu x expected value of y. And now I've just written down every possible cross product. Everybody comfortable with what I just did? I skipped a lot of steps, but basically I just took this ugly thing and did all the cross products. Now, this on the board right here is the same, if they're independent, as expected value of x, expected value of y. So this thing right here is 2 mu x mu y. And here's another 2, mu x mu y. And here's a minus 2, mu x mu y. And here's another minus 2, mu x mu y. Oh, look! Poof! QED. Okay? So basically all the ugly cross products disappear, but only if expected value of x, y is expected value of x times expected value of y. This is the one place I used independence. If they're not independent, this stuff does not all cancel necessarily. Okay? This we're going to use all over statistics. Statistics uses this everywhere. That if you do some arithmetic with random stuff, if those things you're doing arithmetic are independent, their means will add and their variances will add. Okay? This is a basic fact that is going to come back for the entire rest of the semester. Last fact. Convolution. Wait a minute. You thought you were done with that. Fat chance. Okay. So, we have this variable called x, and we have this variable called y, and then we have this new variable which came from summing them. So, the probability that z equals some particular value little z Z is a random variable. Probability takes on a particular value. Well, how does it get that value? It gets that value because x plus y added to that value, because z is x plus y. And there are lots of x's and y's that add to the value z. Z comma 0, 0 comma z, z over 2 and z over 2, 3/4 z and 1/4 z. There are lots of pairs. Remember the roll of the dice? How did you get 7? You got 1 plus 6, 2 plus 5, 3 plus 4. This is the same thing, just in continuous math. So in continuous math means we can't just add them, we have to integrate them. So it is the integral of p of x, px of x, py of z minus x, d. Yeah. Okay, I used the value of x. That's kind of ugly, but that'll work. This is all possible pairs of, let me make sure that that's a y. This is all possible pairs of the value of the random variable x and the value of the random variable y, such that pair adds up to the value little z. Right? So z 0, 0 z, z over 2, z over 2. This is all those possible pairs. And all of those will give us this value. So the probability of getting this value is the probability of summed over all those pairs. But look at the integral we got here. That's the definition of convolution. That's take this curve, which is the density of x, px, x, and take this other curve, whatever the hell it is. We got two random variables, so I'll just give it some other shape. And this is py. And what do we do with the two curves? We take this curve, flip it over, and do dot products in order to get this curve as a function of various z's. That's convolution. It's the same thing, which means there is, in fact, we won't do it that much in this class, hardly at all beyond this, but there is this intimate connection between Fourier analysis and probability theory. One of the ways people in an abstract probability theory course will talk about ways to summarize a probability distribution. One of the things they use is something called, I think it's called the characteristic function, which is the Fourier transform of this. Why? Because when you sum things, it's convolution, which is hard to do. But you can take their Fourier transforms and multiply them. Use the theorem that we used at the end of linear systems theory. Okay? So there's a connection between the two. And then one place we're going to use that connection is talking about the Gaussian distribution, for which we use this convolution fact, and we already know how it works. So we'll get to that in a moment. Yeah, I was going to say, we acted like, so one of those intimate, I got to hold that until this slide, in fact. Okay, so now let's return to the bell curve, which we've alluded to but not really done the details of. The Gaussian distribution is ridiculously useful and is also in many ways inevitable, as we'll talk about as we proceed through the rest of today. Now, we talked about the Gaussian back when we did linear systems theory as just one of our examples of a function and how does it behave and what kind of filter it is. Okay? And we, at one point, alluded to what happens when you blur, some function by a Gaussian, and then you blur it by another Gaussian. So that's convolving two Gaussians. What we've just learned on the last slide is if we have a random variable that has a Gaussian distribution and another one that has a Gaussian distribution, and we add them, the densities convolve, which means the same thing that happens in linear systems theory, blurring by two Gaussians, which it turns out gives you just Gaussian blur that's blurrier, is the same thing that will happen if you add two random variables that are Gaussian. They will get a higher variance. How much? By summing the variances of the two guys you started with. That's the thing I just proved. So there's this intimate connection between thinking about, signals and Fourier, and thinking about probability densities. That can be useful. It makes some things easier to prove in one domain than in the other domain. Okay, So now, let's start talking about Gaussians. So here's the formula for the standard bell curve, univariate. It is how far am I from the mean? So mu will be the mean of the distribution. The density of any given point is how far am I from the mean as multiples of the standard deviation, sigma. So x minus mu over sigma is how far is x from mu in units of sigma. Take that, square it, divide it by 2, take an exponential, and then multiply by a constant so it integrates to 1. Okay? So this constant is just required in order to get the thing to multiply it to 1. And yes, one can go off and do the calculus to prove that. I will not do that here. Some things fit really neatly, so that if I make this thing twice as wide, I need to make it half as high, so that it integrates to 1. If it integrated to 1 before, if I make it twice as wide, I'm going to make it half as high. This formula does that, because if I make it twice as wide, I'm doubling sigma. So I'm taking x minus mu over 2 sigma as my distance function. Okay? And so if I double sigma, I've also doubled the sigma on the constant. There's a square root here, so I've doubled the denominator, meaning I've divided the height by 2. If you widen it by 2 in here, you will simultaneously halve the height over here. Okay, so that's good. It's behaving reasonably. But again, this just looks like math, but I'm trying to get you to think of it as a distance function. I'm going to say the probability of any value coming up has to do with how far away it is from the mean. You can see that this thing is symmetric around the mean. If I go a distance to the right or a distance to the left, I get the same answer. It only depends on the distance. Okay, so it's a function of the absolute value of x minus mu, or x minus mu squared, which gets rid of the worry about the sign. Okay? And since sigma is squared, another way to think about it is it's a function of x minus mu over sigma. It is a function of that. Okay? How far is the data point we're talking about from the mean in units of the standard deviation? And it turns out, by the way, mu is the mean of this density, and sigma is the standard deviation, the square root of the variance of this density. Sigma squared is the variance as defined the way we defined it a couple of slides back. Okay, so this function happens to have this shape, and if you change the mean, you're just sliding it left and right. And if you change the variance, you're just making it wider or narrower. Okay? It always has the same shape. Now, we've been talking about multivariate, which means we need to have an extension of this to the multivariate case. And so the extension of this is pretty ugly looking, so I want to take apart so you know all the pieces. And let me do that and then do the break. So, what are the pieces here? There's a constant out here, and the constant makes it integrate to 1. Multidimensional integrate to 1. It's now a function of a random vector, which has a expected value, which is a vector, and has a C, not C inverse. C is the covariance matrix. It's the expectation of the outer product of x with itself, just as it was 2 slides back. So all the elements we've defined before. It has a constant that makes it add up to 1. In 1 dimension, that's 2 pi sigma squared. In n dimensions, that 2 pi gets raised to the number of dimensions, square root of 2 pi to the same number of dimensions. So each time you do it, you have to do it in a new dimension, so another factor of 2 pi comes out of the math. And then I have to say, well, how big is the variance? Well, that's complicated because the variance is a matrix. So what do you mean by how big is a matrix? Well, we did all of linear algebra incredibly fast in this class. We didn't do a semester of linear algebra. In a semester of linear algebra, you'd have weeks on what do I mean by the size of a matrix. The fancy word for that is its determinant. One way to think about the determinant is just an intuition. It's a mathematical fact. But let's do the 2D version just so you have a feel for what a determinant is, and so you'll understand the next thing I'm going to talk about, just so you have a way of thinking about determinants. Now, obviously, you're in MATLAB. You have a matrix. You could just say det of C, and it'll just hand you the number back. Fine. But what's it mean? Okay. So, if you take a matrix, and we're sitting in, let's go 2D matrices, 2 by 2 matrices, a matrix will take a point and move it somewhere else. and take another point and move it somewhere else. And take another point and move it somewhere else. Which means if I took a little teeny square and I went over here, it's going to do something to that square. Now, in 2D, well, in matrix in general, 2D is really easy to understand. What we do understand really well in this class is the SVD. And what's the SVD going to do? It's going to take my little square and rotate it to somewhere else. Then it's going to stretch the axes, so my square will not be a square anymore, it'll be a diamond. And then it's going to rotate it somewhere else. So this guy is going to end up being this, somewhere. Okay? Let's say this little box is 1 by 1. It has area 1. This new box has some length here and some height. It's got a new area. What the new area is the determinant. Determinant is big if squares get enlarged. Determinant is small if squares get smaller. The determinant's allowed to be negative, and the negative means the square got flipped. We don't care about the negative because, in our formula here because we're taking its absolute value. Okay? So the determinant is basically the size of the matrix, meaning are the numbers big, meaning it's taking little squares and enlarging them, or are the numbers small, is it making them smaller? So just an intuition about the determinant is, it's a number that comes out of matrix algebra that says, does it enlarge things or make them smaller? One more second. We also know the SVD. And the SVD says a matrix is a product of 3 matrices. One's a rotation. What does a rotation do to the area of a square? Nothing. So its determinant is 1. What does the second rotation do to the area of a square? The V instead of the U. Nothing. Which means the determinant is how much does the singular values change the area of a square? Or of a cube, or of a 4-dimensional thing. Well, the singular values are a diagonal matrix. They just take things and stretch them and squeeze them. So if the first one changes the value of the area by that singular value. The next one changes the area by that singular value. So for the people in this class who've never seen a determinant before, the determinant is the product of the singular values. Okay? So I've given you a way to calculate the determinant. You don't need to do that because you can just call det in MATLAB and it'll give it to you. But it's the product of the singular values. If I'm making everything bigger, you get a big determinant. If I'm making everything smaller, you get a small determinant. So this is, the covariance matrix is something that basically stretches my distribution, after I've rotated things in some simple way with the SVD of the covariance matrix. I'm taking some axes and giving them a big variance, and some axes giving a small variance. So I'm taking those principal axes, the principal components, and I am multiplying. I stretch sometimes, I squeeze sometimes. What's the product of all those stretches and squeezes? So that's what this is. So there's a bunch of math behind it, but the intuition you actually already understand. All right? Up top here, this used to be x minus mu over 2 sigma squared. So the over 2 is sitting right there. The x minus mu is now a vector x minus mu, so how far am I from the mean? But now I've got not just in units of standard deviation, now I've got in units of the covariance matrix. So this is the inverse of the covariance matrix, c to the minus 1. So it's as if I had the sigma squares downstairs, but it's a matrix, so our equivalent to being downstairs is to take an inverse. Okay? And so it's how far am I from the mean in units of the covariance matrix. We'll get back to this intuition many times in future, but here's an example of a 2D Gaussian. I've drawn an ellipse here. Why have I drawn an ellipse here? Because upstairs here, set that equal to a fixed number. Say, when is upstairs stairs equal to, say, 1 or 1/2? And then plot what things that cause this exponent to be that one value of, say, 1/2 or minus 1/2 or whatever number you pick. Well, this has all the xi's. This is a bunch of constants. This is a bunch of xi's, which is to say, by the time you do this matrix multiply, this is a quadratic. And this quadratic set equal to a constant is an ellipse. You will, in some homework assignment, definitely be asked to plot this ellipse. Maybe you already did earlier on in the semester in another context. It's the same math. Okay? And so, when I've moved this way, I've moved 1 standard deviation. When I've moved this way, I've also moved 1 standard deviation. I didn't move as far, but that's because this particular distribution is correlated. It's not independent, right? The way I've drawn it, it's tipped. X depends on y depends on x. But if I move this far, I've reduced probability by the same amount as if I moved this far. So that's what the exponent's doing. Okay? So we're going to examine lots of consequences of this formula coming up, but let's take a break. See you in 3 or so. Okay, everybody, let's get back to it. Yo. So, we have the formula of the multivariate Gaussian. It's the things that we've been seeing pictures of. Every way you slice it, as we'll talk about momentarily, you get a Gaussian. The thing about a Gaussian is once you're in Gaussian land, you have to work hard to leave it. Because almost anything you do with this, you still have a Gaussian, as we will discuss. So let's start talking about why the Gaussian is a friendly, useful thing. It is your friend, even as daunting as the second formula might look to you right now. Okay, so if you have 2 or n variables, but let's talk about 2 since we're using the word ellipse. If you have 2 random variables and they are independent, that means the probability of x times y is the probability of x times the probability of y. And if it's Gaussian, that means we've got a Gaussian in x and we have a Gaussian in y, because we have this formula, but for it to be independent, we can't have any x times y's in there. So we have x times mu x squared plus y times mu x squared. Mu y squared, I'm sorry. Okay, in this formula. Which means that the formula will split up. What did I do with my good black one? I moved it. Oh crap, I don't know which one is the good one. The random one. So if it's independent, so that the p of x comma y is p of x, p of y, then it's going to be, some constant, going over square root of 2 pi, etc. stuff, e to the x minus mu x squared over 2 sigma x squared, e to the y minus mu y squared over 2 sigma y squared. Independent means p of x times p of y. Okay? This is a Gaussian, a bell curve in x. This is a bell curve in y. Now you can ask, when does this equal to some constant? So for example, what are all the places that have probability density 1/2 or some value? Just C. Okay? What's the locus look like? Well, that locus is this product, or otherwise known as e to the exponent x minus mu x squared over 2 sigma x squared plus y minus mu y squared over 2 sigma y squared. I've just combined the exponents. What's the locus of that equals some constant? That is a formula for an ellipse. Centered on mu x, mu y, where the aspect ratio is sigma x over sigma y. Okay? That just is an ellipse, because what's an ellipse? An ellipse is x over c sub x squared plus y over c sub y squared equals some other constant. That's an ellipse. And so this whole thing equal a constant is the same as the exponent equals a constant, and the exponent is exactly the formula for an ellipse, except shifted over to centered on mu x, mu y. So joint density of independent Gaussian random variables will be elliptical. Conditionals of a Gaussian. So first of all, let's do that. So conditionals. So if we have some Gaussian that, let's just deal with 2 variables for the moment, but it's this second formula. So we've got any old bivariate Gaussian, not necessarily independent. Now, any old bivariate Gaussian, by the time you figure out what's sitting upstairs in the exponential, it's minus 1/2 times this form. This is a bunch of constants. This is x minus mu. By the time you multiply it out, it's a quadratic. Okay? Now, if I make it conditional, so this x vector is x comma y. If I set y equal to a constant, which which is what a conditional is. Fix the value of y and see what we have left and renormalize it. So I fixed the value of y. So the y's now in here are all constants. So now I have a quadratic in x. So I have e to a quadratic in x. E to a quadratic in x is a Gaussian. This is a fact we use over and over again. If what you have upstairs in the exponential is a quadratic, you have a Gaussian. And to turn it into a Gaussian that actually looks like this form or this form is just move all the constants around, pull constants out, and futz around until it gets this form again, which you can always do. And I'll show you examples of that in a subsequent slide to get a feel for how you do that. But basically, if you have e to the quadratic as a probability distribution, it is a Gaussian. Getting it into a form where you figure out what c is and what mu is takes some algebra, but it can always be done. So that's number 2, is that if you take a Gaussian and you slice it, you still have a Gaussian. And going back here is a 2-dimensional Gaussian. Every time I slice it, I have something that looks kind of bell curve-ish. Down here it looks bell curve-ish. Up here it looks like. Over here it looks bell curve-ish. Over here it looks bell curve-ish. Okay? It is. Okay? As we'll see in a subsequent slide, but while we're saying it, you can also slice it other ways. Not just parallel to the axes. It still works. Marginals. If I take a 2-dimensional Gaussian and smash it down on the axis, which means I take this ugly formula and I integrate over y, leaving x. By the time I'm done integrating over y, I'm still going to have an exponential in x. And it's going to be a quadratic upstairs. So I'm still going to get a bell curve. Obviously, for a separable one, like this one, it's obvious. If I take the marginal for x, all I'm doing is getting rid of this. And what I have left is a Gaussian. Okay? But even if there's a covariance matrix in there, even if it's not separable, not independent, it's still the case that by the time you integrate out the y's, you end up with a quadratic upstairs. So easy next to all these is that the math is easy if you want to go through the whole rigmarole of proving it. Product of 2 Gaussians. So suppose I want to do Bayes' rule. Okay? And it's in a multivariate context. So I want to do, P of I should use P of x given y, P of y. And there's going to be something downstairs which I'm going to ignore for the moment. Suppose the top 2 guys that we're doing in Bayes' rule happen to be Gaussians, multivariate Gaussians. Okay? And so you have these things that are functions of vectors, both of which are Gaussians. And you need to multiply them for whatever reason. Okay? And so you got this guy, which is some constant, times e to the minus 1/2 quadratic. And then you got this guy, which is some other constant, e to the minus 1/2 quadratic, where quadratic is quadratic in your vector. Well, if you're going to take this quadratic and add it to that quadratic, you can get another quadratic. And what I keep telling you is, if you have a quadratic in your vector, one can do some algebra and turn it into this form, always. If it behaves like a distribution, so it's got to be going down, so the x squared terms have to have negative signs on them. That part is a fact, right? Because if they had positive certain signs on them, it would be going up, and the density can't do that. So as long as the quadratic, all the squared terms, x squared, y squared, and x times y, all of those have to have negative signs on them. As long as that's true, you can always turn it into this form. Okay? And I'll do a version of that for one case. I won't give you the general how do you do that math, but it's kind of ugly, but you can always do it. Sums of random variables are Gaussian. This one's harder. But how would we intuitively prove it based on stuff we've done this semester? So in 1D, if we add 2 1D Gaussian distributed random variables, the probability density function of the resulting random variable, how do you get that from the ones you just had? Something I said about 20 minutes ago. Say it louder, I heard somebody say it. If I've got P of x and P of y, and I add the random variables x and y, what do I do with P of x and P of Y to get P of random variable X plus random Y, variable Y. What do I put here? Yeah, convolution. And the convolution of two Gaussians is a Gaussian. It just is. I mean, you could do the math of it, meaning write the convolution formula and the double integral, no, it's actually a single integral, and move things around and realize that that's what you get. No need to do it. You blur a Gaussian by another Gaussian, you get something that's blurrier. Not only that, we've also already proven that the variance is add, and so that all that happens when you blur a Gaussian by a Gaussian is you take the covariance matrices and you sum them. The first one's got a covariance matrix, second one has a covariance matrix. Those two matrices just get summed. Okay? Very easy math. And the mean sum also. So the mu of the sum is the sum of the mu's, and the C of the sum, not the C inverse, the C of the sum is the sum of the individual C's from the two guys that you were adding together. Okay, so that's that. This I'm not going to prove. I'm not even going to define all the terms, but I just want to talk about it. Suppose you are trying to model some, interesting statistical domain where you know the mean for whatever reason, or you want the mean to match a given thing, and you want the variance to match a given thing, and that's all you know. You have no idea what the density is. So if you tell me the mean and the variance of some random variable, you haven't told me a hell of a lot. So here's, a Gaussian centered on mu with sigma. Okay? That's a density that has that mean and that has that sigma. So is this. So is this. So is, I'm sure there's some binomial with just a spike over here and a spike over here that has the same mean and variance. I'm sure there's a uniform distribution that has the same mean and variance. I could just stretch the thing until it comes out just right. There's an infinitude, an uncountable infinitude of densities that happen to have mu and sigma. So if you knew mu and sigma and you knew nothing else, what basis would you use in modeling to pick one particular distribution? One basis that you might pick is knowing as little as possible about the density otherwise, meaning when I give you a datum drawn from that sample, from that density, and I just give you one datum, how much is that telling you about the density? And so how many bits do you learn? So this metric of how random is a distribution comes from information theory. This course does not teach information theory. You're going to need to pick that up in some other course. Probably something Larry Maloney teaches. Perhaps he does that every once in a while. But information theory, invented in the 50s, was this notion of taking random events and noisy communication channels and talking about how much information is present or how much information has been transferred. And the information transferred from one sample of a density, there's a formula for it. It's integrating p times log of p, where p is probability density. Okay, whatever. There's a formula. The units of the formula, once you integrate it out, are in bits. Bits as in, you've given me one bit of information. I can make one yes-no decision that I couldn't make before. And so what you might want your density to be, if I only know these two facts and I know something else, I don't know anything else, is to have maximum ignorance about everything else. And ignorance needs a metric. And the metric is entropy that we usually use, which is in bits. And the max entropy distribution, given a mean and a variance, or in multidimensional vector mean and a vector covariance, the max entropy distribution is Gaussian. So it's kind of a standard thing to use. Lastly, I'm not going to prove it here, but we're going to use it as a fact quite often, is that the Gaussian distribution is inevitable. And what I mean by inevitable is, if you take a random variable that doesn't remotely look Gaussian, as long as it's well behaved, for example, it has finite variance. If you take some random variable and you take a sample from it, take another sample from it, take another sample from it, and then you calculate the average of your samples. You do this over and over. So you're summing identically distributed independent random variables. So just multiple draws from the same density. So you may start out where the first draw, its density is the one you gave me, which doesn't look Gaussian at all. It could be exponential, flat, binomial, I don't care, just some other density. But if I over and over again sample a thing and then take the numbers and add them up, you divide by n and compute an average or not divide by n, this is relevant. But the more you do this, the more the resulting thing is going to look like a Gaussian. Example. Roll dice. When you roll dice, you start out looking like this. 6 values, all equally likely. If you roll 2 dice and you add them, you've seen that distribution. It looks like this. Right? You've seen that in a previous picture. If you add 3 dice, it's going to, look even more like a Gaussian. If you roll the dice 5,000 times, it'll look really close to a Gaussian. It won't be identical because it's discrete and a Gaussian's continuous, but it'll get closer and closer. Another example, not dice, but coin flips. So take a coin. Suppose it's not even a fair coin. It's a 3/4, 1/4 coin. Okay? And so we're going to treat the coin like tails is 0 and heads is 1. And it's coming up tails 1/4 of the time and heads 3/4 of the time. So that's the density we started with. It doesn't look anything like a Gaussian. We flip the coin 2 times, I can get a 0, 1, or a 2. I flip the coin 3 times, I can get a 0, 1, or 2, or a 3. By the time I flipped it 500 times, we get a density that looks a hell of a lot like a Gaussian. Centered on, what did I say, 500 times? I forget. But centered on 500 times 3/4. Or whatever the mean of this is, sorry. Not 3. Yeah, 3/4. Okay? With a density, with a variance that'll come from the sum of the variances of this. So if it's the same guy 500 times, it'll be 500 times the variance of this. So the central limit theorem says anytime we collect a bunch of data, a bunch of trials of collecting spikes from a neuron, a bunch of trials of a human in an experiment pushing this button or that button, a bunch of trials from someone twisting a knob in order to null the motion in some stimulus. I don't care what experiment you do, but if you run the experiment multiple times and make the hopefully reasonable assumption that your trials are independent of each other, then no matter what the distribution is of the thing you started with, by the time you start computing descriptive statistics, like the sample mean, that the sample mean will look like a Gaussian, even though the individual data don't. And so the Gaussian sort of inevitable, you can't avoid it because all the stuff we do by describing the results of our experiments generally involve taking averages of multiple trials. And so no matter how badly distributed, badly meaning not bell curve-like, the original data were, by the time we average them, they will. And so we can use the properties of the Gaussian, all these other nice properties of the Gaussian, for things like calculate the average of my data. So the Gaussians can come back again and again and again. So now let's talk about things that you can do with the Gaussian. So, suppose we've talked about taking a distribution and smashing it to one of the variables called the marginal. Okay? So how do you do that with the Gaussian? So the Gaussian, we had the formula before, which was e to the minus 1/2 x minus mu inverse covariance x minus mu. Okay? That was the formula that's not on the slide right now. So remember, it was the inverse covariance matrix. So let's call the inverse covariance matrix, let's give it a name. It's called the precision matrix. So variance means things bounce around. Precision means things don't. So small covariance, the inverse covariance matrix, will have big numbers. So the numbers in a precision matrix are saying, how precise are you in this direction or in this direction? And when there's covariance, as there is here, there'll be non-diagonal elements in the inverse matrix, just like they are in the covariance matrix. You'll have a sigma xy. Okay? So you have x. So upstairs in the formula for the Gaussian, the Gaussian, the p of x comma y, x1 comma, I got to use the terms that are on the slide. Yeah, it's x1, x2. So p of x1 comma x2 is the normalizing constant, e to the minus 1/2 x1 comma x2, that's the vector, minus mu1 comma mu2. Yep. The matrix, which is the inverse covariance matrix, which now I'm going to call precision, P11, P12, P22, P12, and these are symmetric matrices, so I'm going to call this guy P12 also. That means P21, but they're equal to each other. And then I'm going to put, I didn't erase enough, the transpose vector over here. So it's going to look like this. Okay, I'll write it this way. x1 comma x2 minus mu1 comma mu2. Okay, that's the formula. But suppose we are going to smash it down on the x-axis. Oh, sorry, I'm doing two things here. Up here we're doing the conditional. Sorry, not the marginal, the conditional. So suppose we're going to do the conditional, picking a particular value of x2. And that particular value is a. So now, this one is going to get replaced with a, and this one's going to get replaced with a. And we do all the algebra of multiplying this by this by this. Okay, so it's a vector times a matrix times another vector. We end up with a number. Okay, so we're going to get x1 times p11 times x1. So we're going to get a p11. Okay, so this is writing it out. That p11 takes x1 minus mu1 and x1 minus mu1. P22 takes a minus mu2 and a minus mu2. That's a constant. We're going to ignore the constants. P12, these guys, are going to take x1 minus mu1 and a minus mu2. Take x minus mu1 here and a minus mu2 here, or a minus mu2 here and x1 minus mu1 here. That's what goes through these two constants. Okay? So that's what's written out here. We're going to not write out all the terms. We're going to leave out all the constant terms and just write in some of them. So what we see is that we got p11 times x minus mu1 squared. We got two versions of p12 of the cross product, and then we have the constant term that we're ignoring. Remember I said, by the time you're done, you get a quadratic up here. So we're going to look and find out what the quadratic looks like when we have done a conditional. We fixed the value of x2, and we're going to say, what's this as a function of x1? Okay, so all we care about is the terms that depend on x1. So this is x1 minus mu1 times a constant, so there's no x1 squared here. The term we left out was all constants, so there's only one x1 squared term at all. x1 squared times p11. That's the only x1 squared term. Okay? Now we look for terms that are linear in x1. So from this term, we're going to get a minus 2 mu1 p11 times x1. We're going to get a minus 2 p11 mu1 times x1. Okay, that's the cross product from this term is sitting here. And then we're also going to get a linear term in x1 here, which is 2 p12 times a minus mu2. 2 p12 times a minus mu2. And everything else is a constant, so we're going to ignore it for the moment. Okay? Now, what is on the next line and why is it there? Oh, I'm sorry. And so now we're going to try to make this look like a normal distribution. One dimension normal distribution. So one-dimensional normal distribution is x minus mu x times covariance times x minus mu x. Okay? That's what we want. So we're going to take this ugly thing and try to put it into this form. Now, one way to do that is to skip all the steps of the algebra that led between those two lines and just notice the following. E to the minus 1/2 x minus mu over sigma squared, which is another way of writing the Gaussian. If you is equal to e to the minus 1/2, multiply it out, x over sigma, sorry, clean way, x squared over sigma squared, x squared over sigma squared, minus 2 mu over sigma times x plus a constant. Which means that the thing that's multiplying x squared is 1 over sigma squared. Over here, the thing that's multiplying x squared is p11, which means that p11 is 1 over sigma squared. So we have now found out what the new sigma is. Okay? The thing that multiplies x is minus 2 mu over sigma. With the 1/2 out here. So the thing that multiplies x, where'd it go? Yeah, the thing that multiplies x is this big thing, which is minus 2 mu over sigma. And we already know what sigma is, what sigma squared is. It's, what did I, yeah, okay, so let's just write that out. Because to me, that's an easier way to do it than getting to that next line, so I'd rather do that. Okay, so the thing that's multiplying x is this thing to, why did I erase what I just had? That was silly. To p12 a minus mu2, p12 a minus mu2, minus p11 mu1. That's the thing that's multiplying x. And what I had in the Gaussian is that should be equal to minus 2, remind me of what I had there. X minus mu sigma squared. The second term is minus 2 mu over sigma times x. Yes, okay. So that's going to be minus 2 mu over sigma. Okay? The only thing that's bugging me is where did I'm getting off by a quadratic. When I did this in my head at my house, I didn't have this tripping up. So give me a second to figure out what it is that I'm doing so silly. Okay, so mu should be, yeah. So mu should be sigma times that stuff. What am I doing wrong that I'm getting a square root that shouldn't be there? Crap. Yes. All right, let me just leave it at that. That's 2 mu over sigma. Let's just do the math. We want to know what mu is. So we can get rid of this, we can get rid of this, we can get rid of the minus sign, but put a minus here and a plus there. Is that where we're headed? Multiply over by the sigma, so mu should be that times sigma. No, that's bugging again. Just damn it. I hate it when I hit moments like this. Alright, let's look at his way of doing it, which is right here, and see if that works, because what I'm doing is coming out wrong. And I can't figure out what my mistake is. Okay, so the x term you're going to get as written here is going to be this one, x11 times this constant, plus this x11 times this constant, which means you're going to get 2 of this constant as what x1 multiplies by. going to come back because I don't want to waste more of your time with me tripping on algebra that I knew, but so I'll come back to it next time. Clean it up. My apologies, but the point is, skipping the fact that I just can't figure out why I can't do this algebra in my head right now, is that this is a quadratic. And you can always write the quadratic and rewrite it as x minus mu squared over 2 sigma squared. And the way you do that is by figuring out what's the constant that's on x squared, what's the constant on x, and then do what's called completing the square, which is to add a constant and subtract a constant from what you got, such that you can put it in the form written right here, which is x minus mu squared times sigma squared. This is done in the univariate sense. You can also do this in the multivariate case if you have more than one variable left. And then you can look at the constants you got, and they'll give you what's the new mean and the new sigma. Now, one of the things that's worth noticing here, so the marginal here is centered on mu1, right? We all started out with the mu1 being the overall mean on x and mu2 being the overall mean on y. The marginal, once you take a cut, is going to be mu1 plus a term that's going to depend on how far, oh, there's a typo, how far a is from mu2. Right? If I take a cut through the middle, the marginal is going to have the same mean as it had before. But if I take a cut from here, the marginal is going to move, the conditional is going to move off to the left. And if I take a cut up here, the conditional is going to move off to the right. That's happening right here. And that's telling you how far. So the reason I'm giving you this is because this allows you to compute conditionals straight out of the precision matrix. Doing this with the covariance matrix is quite ugly, as you might imagine, because these numbers come out of the inverse of the covariance matrix, so they're ugly formulae. But from the precision matrix, that's what's upstairs, and it's just multipliers. Okay? So let me write myself a note to fix the typo and to come back to you possibly in an email rather than in a class, but we'll see on fixing the algebra. Okay. You can't get away from anything being a Gaussian, which is to say, the marginal is obviously a Gaussian, because that's just delete y, integrate over y, and just look at x, and it's now a formula in x, and it's a quadratic. But it turns out you can also project smash in any vector direction you like, and you still get a Gaussian. Why is that? Because what do I mean by smashing it down this way? It means I'm going to take a random variable x and, where are we? Okay, so what's z? Z is I take any place in this two-dimensional world and I dot it with a unit vector. I project it onto a unit vector. So the unit vector is pointed this way. Is this a build? Because I remember the unit vector being there, but I don't see it. Oh, it's down here, right? So here's a unit vector. If you take a dot product with this unit vector, you're taking all these 2D places and projecting them onto this line. And if you're asking what's the probability of that, you're integrating over these things. But what is projection? Projection is a dot product. What's a dot product? It's some number times x1 plus some number times x2. It's a linear combination of the two coordinates. And so that linear combination, so some number times x1, its density function is going to be the density function you started with, except you're multiplied by a constant, so its mean is going to change multiplied by that constant. And its variance is going to change by that constant squared. It's going to be a Gaussian, because all you've done is, stretch the axis. The second one, mu2 times x2, is just a constant times a Gaussian random variable. It'll still be a Gaussian random variable. What's mu1 x1 plus mu2 x2? That's the sum of two Gaussians, which I've already told you is Gaussian for obvious reasons, because it's still a quadratic upstairs. So you're going to get a Gaussian no matter which way you project. The Gaussian is a density that only has two parameters. What's its mean what's its covariance? Or in this case, since we're talking about one-dimensional thing, what's its mean, what's its variance? And we know what its mean and variance are because we have formulas for that already. Right? These don't look exactly like 4 slides back, but they are. This is a weighted sum of things, and the mean of a weighted sum is the sum of the means of the individual guys. And so this is a fancy way of writing the same thing. And what's the covariance or variance when you take a weighted sum? So that's, you got to put the matrix transpose on one side and the matrix on the other side. We were projecting, so now we've got the transpose on the left. I think last time we had it on the right, but it's in the right orientation to do what we want. Okay? So this is using exactly what we already said, which is for any distributions don't have to be independent. The sum of the means is the mean of the sum is the sum of the means. The mean of the sum is the sum of the means. And the variance or covariance of the sum is the sum of the covariances, or the, if you apply matrix, you apply matrix both before and after. Okay? So all this is the same rules we had before. So this is this notion of not being able to escape a Gaussian. Okay, for the minutes remaining, I want to go back to the notion of covariance and correlation. So, last time Arrow taught, he spent a lot of the class talking through the linear algebra of covariance and correlation. Remember those vectors and what's the angle between them, and the angle could, obviously, if you take its cosines between 0 and 1, and that's the correlation number, and that you end up with sigma xy over sigma x when you're dealing with data. These are all formulas you saw for samples. So the same math applied to these abstract probabilistic entities gives you all the same answers. So covariance I've already defined as this. And so you can another name for covariance if it's 2 variables is sigma sub xy. And then if you normalize the length of the vectors before you calculate their angle, which you did with data, now we're doing it with full continuous distributions. Then you get a number that's like the cosine of an angle. It's a number between 0, -1, and +1. +1 meaning if you tell me x, I already know y. No doubt about it. -1 meaning if you tell me x, I know y, but if x increases, y decreases. And numbers between there say, when you tell me about x, I'm learning about y, but I'm not learning everything. So this is it for probability distributions. This is what you saw, although written in the ugly summation notation for samples. The only thing that should look new to you down here are 2 things. One is, I mentioned without writing it down, that when you meet this in textbooks, you're going to see a different notation for populations or for probability densities than you see for samples. And the notation you'll see for probability distributions is things like Greek letters, mu for population mean, sigma for population or probability distribution standard deviation. But you're going to see letters for samples. So rather than mu for a sample, you usually write x bar, meaning the sample mean. And rather than sigma, you usually use s for the sample standard deviation. That's one new thing that's on the slide. Anybody spot what the other new thing is on the slide? Which is really kind of a forward pointer to a little bit later in the semester. What changed from what Arrow had on the board? n-1. Okay, he had n down here. Now, should we take the outer products of deviations from the sample means and adjust them by n or by n-1? Well, answer, it depends on what you want. If you're in a frequent statistics class, if some of you took stats as undergraduates, you would have seen n-1s all over the place. And for some sample statistics, you might have even seen n-2 or n-3, where the thing you're subtracting is degrees of freedom. We'll return to that concept in about a week and a half. We're going to do a very, very brief tour of frequent statistics in this class. But whether you want n-1 or n depends on what you're trying to optimize, what you're trying to learn about. And we'll return to that concept later. So I'm not trying to tell you it here, I just want you to be aware. You don't see it here because in the correlation formula, whether you used n for this and n for this and n for this and n for this, or whether you used n minus 1 for this and n minus 1 for n minus 1 for this, they all cancel. So the correlation formula doesn't care about this thing, but the sample standard deviation does. Okay? But the idea is that we have these kind of separate sets of notations that you'll run into, so I just wanted you to be exposed to them. But now let's talk about the meaning of them. So correlation, as you learned with data, and so we're back to data for a moment here, was something about the shape of the cloud. If they all fell perfectly on some line, then they're perfectly covariant. The big long vector in data space of x and the big long vector of data space of y are pointing in exactly the same direction. Their angle is 0, the cosine is 1. So if they all fell on a straight line, that's a correlation of 1. Correlation is telling you how much do they vary together. If they don't covary at all and you just have this circular cloud of dots, that's no covariance, no correlation. Correlation is 0. So correlation is telling you something about that. The formula is taking how far am I from the mean times how far you are from the mean and multiplying them. That product, if we center things on the mean, that product says numbers in this quadrant, the x minus mu x is positive, the y minus mu y is positive. So numbers in this quadrant will contribute to that formula with positive numbers. Things that are less than the mean on this axis and less from the mean from that axis, their x minus mu x times x minus mu y will be a negative number times a negative number. They will contribute positively to the correlation or to the covariance. The other two quadrants contribute negatively. So the more stuff you have this way and the less stuff you have this way, you get a positive correlation. The more stuff you have this way, the less you have that way, you have a negative correlation. That's just what the formula gives you. So that contributes positively to it. And this contributes negatively to it. Sorry, it's a cute Pascal-Walsh type build. Okay, so we use that. The other thing is let's go back to regression. So when we did linear regression, we had a variable and we had a variable. And we did various kinds of regression. We had a number where we calculate our errors perpendicular to the line. That was called total least squares. And it points down the largest eigenvector of our data. But we had least squares regression, where we did x dot y over x dot x as our, and that arrow a week ago converted that into what that basically is sigma xy over sigma x times sigma y. Okay? And that's predicting y given an x value. So if you tell me somebody's IQ is 130, then, well, I got a cloud of dots over here, which is not the same as the whole cloud because the cloud is correlated. And the middle of the cloud of dots over here is, $140,000 a year expected income, if you believe this, whatever. And so this is predict y from x. Now, this is a random variable, and this is a random variable if you pick a random person. So one could also say, what's your income? Okay, I'm going to predict your IQ. So if I said 140K, now I've got this cloud of dots, whose mean is over here, and I would have gotten a line like this. So regression lines, if all the data were on this black line, on the TLS line, all of them were there, perfect correlation. But if you tell me IQ, I know income. If you tell me income, I know IQ. But because the line is all spread out, if you tell me IQ, I know income, but I don't pick the black line, I pick the red line because there's a lot of variability here. And so the more uncorrelated they are, the more the red line is going towards the horizontal, a term called regression to the mean. And if you regress in the other way, meaning tell me their income and I guess their IQ, so now I end up on this line, meaning this cloud of dots, this marginal cloud of dots, the center of it's over here, that's my best guess. And so I regress to the mean of the y's, of the x's when I'm predicting x from y. And I regress to the mean of the x's when you ask, sorry, I keep saying this backwards with regard to my marker. If you give me the x and say predict y, the more uncorrelated they are, the more I'm regressing to the mean of the y's, meaning x isn't telling me that much. The more uncorrelated they are, if you give me y and tell me which x it is, the more I regress to the mean of the x's. Meaning, if they were totally uncorrelated, telling me y would tell me nothing, and my best guess would be the mean of the x's. And so you get a different regression line if you regress y on x than if you regress x on y. And correlation says how much is the angle. Now, this is like a slide that I showed you. These are correlation coefficients and Gaussian dot clouds that correspond to them. Okay? No correlation, some more in the negative and the positive directions. Okay, so that's what correlation tells you. But what it doesn't tell you is the slope of the regression line, because total least squares for all these guys is a regression like this, and total least squares for these guys is a line like this. But the regression line keeps going down towards horizontal as the correlation goes down. But the other thing is we've talked about a concept called independence or dependence, and we've talked about correlation. They're not identical concepts. So here's what I showed you before. Here's a bunch of dot clouds, all of which have a correlation of 0. Meaning you do that thing, and if I want to fit a line to it, the best line I can fit for every single one of these data sets is 0. But on the other hand, if you tell me x is 0, do I know something about y? Yeah, I know it's either a big positive number or a big negative number. If you tell me that y is plus 2, do I know something, x is plus 2, do I know something about y? I do, but I know something different now. It's probably near 0. Okay? This is not independent. I'm telling you something, conditional distributions are not all the same as each other. This conditional distribution is near 0. This conditional distribution is bimodal. Has a mode over here and a mode over here. This same this way. Every single one of these is not, well, actually, this one is independent. This one looks like it may be a product. But all the other ones clearly are not p of x times p of y. But they all have a covariance or a correlation coefficient of 0. So correlation is really about how spread out are they around a straight line. It's a particular model about how two variables go together. A straight line through the means is what correlation tells you about. It does not necessarily tell you independence. So here are 4 data sets, all of which have all the same summary statistics. They have the same mean. So it's just this set of dots. If you calculate the sample mean, and you calculate the sample standard deviation in x, standard deviation in y, and correlation coefficient, they all have the same sample statistics. But this looks like what you mean by saying, here's mu x, here's mu y, and here's the correlation. And none of the rest of these look like that. This is perfect dependence, at least as far as the sample is concerned. Y is a function of x, it's just not a straight line. This is, oh, it actually is a straight line, except somebody should find out who collected those data. And there's probably a problem there. This is an outlier. It's the kind of thing that you would have used our fancy techniques in linear regression to downweight this outlier. And this is, I don't know anything. Because I ran a terrible experiment where x was the same for every data point but 1. And I can fit a straight line, but I certainly shouldn't trust it. Okay? So the point is, multiple points. One is, look at your data. Don't just compute sample statistics. Look at your data many number of different ways that you can, because sample statistics may mislead you. You can get all kinds of stuff with a set of sample statistics, so this is just for fun. Everything up there has the same set of sample statistics, bivariate statistics now, right? So that dinosaur and this pair of ellipses, if all you do is look at x bar and y bar and correlation, you have not learned what your data look like. So look at your data. Okay, this is a repeat. Oh, what? Yeah. Okay, so last bits before we end. I'm going to go a couple minutes over. When you collect sample statistics in multivariate, and you get a correlation or covariance matrix or whatever, and you ask, for my data in these multiple dimensions, how correlated are they? And Now you decide that I'm going to collect more data on my subject. So I'm going to collect 5 variables rather than 3, or 3 variables rather than 2. And all of a sudden, things look less correlated. So it turns out that if I collected data sets that were random in n dimensions, meaning I just make a random vector in n dimensions and a whole bunch of them, and I do this as a function of n. So I make data vectors in n dimensions that are just totally random matrices, lots of data, number of dimensions. So I get these data vectors, and I correlate them with each other across dimensions and ask, what do I usually get? So it turns out that a random vector in n dimensions will give you a correlation coefficient that looks more and more like 0 on average, closer to 0, than if I do it in lower dimensions. So that uncorrelated is favored with random data the more dimensions I have. Now why is that? Well, the way you get the correlation coefficient is by taking the cosine of the angle of the data vectors. So if I pick a random data vector and say, what's the angle between them? So first 2 dimensions. I take a random vector and another random vector. So let's skip the first vector and just have it point towards, well, up. Now I'm going to pick another random vector. Any angle is equally likely, so the angles between the 2 vectors are going to be random between 0 and pi. Right? Just look at that. If I pick a random vector, it'll be equal. So now let's go to the sphere. So I'm going to pick one data vector. So for the hell of it, let's have it point up. Now I'm going to pick another random vector. We don't care about its length, we only care about angles. So I'm going to pick uniformly over the sphere. Well, there's a lot of guys at the equator. There's not that many guys pointing down or pointing up, which means the chance of orthogonal is much higher, or near orthogonal is much higher. So this is the distribution of angles on the sphere. And as you go to more and more dimensions where I can't, point at it in the room, the probability of a randomly chosen angle being close to perpendicular just gets higher and higher and higher the more dimensions you have. So interpreting the correlation coefficient gets a little bit confusing in that space, which means going off and looking for correlation coefficients and imagining that correlated means something and uncorrelated means something vis-a-vis dependence is silly. So if you go out and look for lots of variables and try to get things that are correlated, you can get stuff like this, or like this, or like this. Okay? If you go search for correlations, occasionally you're going to find that silly. Last thing I want to do is take just a couple of minutes, is, again, to hit on correlation does not mean or covariance does not imply A caused B. So suppose I get a positive correlation between 2 events that I'm measuring, and think, oh, well, maybe A is causing B or B is causing A. Well, first of all, the fact that they're correlated doesn't say that A happened first and B happened later. You need to know something about the timing. Causality has to be future in time. But even if that holds, it may be that A doesn't cause B directly whatsoever. There could be some hidden variable that you're not measuring is causing both of them. Happens to have positive correlation with both of them, and this guy therefore inherits positive correlation with each other. Okay, well, I'm going to skip this bit, which is one can write down that in a 3-variable precision matrix and see that that comes out. I'm going to skip that. But the point is that the probability of A and B given H could be the probability of A given H and B given H. In other words, A and B are conditionally independent. If you know H, A happens randomly and B happens randomly, and these guys are in fact independent of each other once you know what H is. This is like the formula for statistical independence, except it's all conditioned on H, so it's called conditional independence. So A and B, in fact, have no statistical relation here, except that which they inherit from H. This diagram over here is called a Bayes net. We often model complex tasks by setting up what depends on what and what's independent of what, where an arrow here means there's a direct dependence. And so this particular Bayes net will give you a correlation between A and B, but they don't actually have a direct one. They inherit it from H. So to do this, you need additional information like the arrow of time, and more generally, it may depend on these hidden variables. A couple other examples of this. This is called Simpsons Paradox. Here's a genetic version. There's also a famous version from UC Berkeley, and I think it was grade point averages across gender, which looked like correlation, where women were getting worse grades than men. But when you partial it out by the department in which they enrolled, they in fact were doing better than the men, but they were picking harder departments or harder grading departments. So here it is in a genetic example, where in fact gene A and gene B are positively correlated, but they look like they're negatively correlated because there's a third hidden variable that we're not talking about that splits things into two separate populations, where this population is low on the, high on gene A and low on gene B, and this other population the other way around. And so you really need to know the whole diagram, where these guys may be positively correlated, but they look negatively correlated because there's something else in there that's affecting them. And so just calculating correlation doesn't answer a scientific question. You have to think about the model. Last example, and we quit. Really stupid example. There's the temperature outside, there's the energy I'm using to heat my house, and there's the temperature inside. So if you have a heating system with a thermostat that's controlling everything, but you didn't know that, and you just go out and take measurements day after day after day of the temperature inside your house, the temperature outside your house, and the energy you're using, and you calculated a covariance matrix, you would get this, which is when the temperature outside is high, I'm using less energy, and the temperature outside seems completely uncorrelated with the temperature inside my house. So you might come up with all kinds of stupid conclusions, like the outside temperature has no effect on the temperature inside my house, and energy spent and dollars on gas have no effect on the temperature of my house, but the outside temperature is somehow affecting how much money I'm spending on gas. So I might as well turn the thermostat off, since the thermostat's not doing me any good. That's silly. And it's silly because you don't have a model about what's happening. And you're just calculating covariances or correlations. So don't do that. Correlation is not causation. It's evidence, but it needs a scientific model. Okay.